Sure. So yeah, hi, I'm a research software engineer at ECM. Yeah, I'm uh, one of the many mentors in this project. So I'm presenting on behalf of, I think, over like seven or so. So this project is the EarthReach project, and the main theme of this project was improving accessibility for graphical information. So we were thinking particularly when designing this project. Oh, sorry,
Just
sorry. That's it. Good, sir. Okay, no, sorry for us. We were thinking in particular of this project of how to improve accessibility for um, graphical information, thinking of people who might have visual impairments or people who rely on screen readers, and also just to reduce the barriers for sharing knowledge in general. So the goal of this project was to um, develop a tool for automatic chart summarization, which would integrate with our plotting tools. And that's what Fomat's been working on for the last months. So he's a machine learning engineer, and he was actually based in Canada for the for when he was doing this project. So I'm delighted that you're actually with us today. You're in person. So yeah, I'll give the floor to him.
Hi everyone. So very glad to be here, one way from Canada, indeed. Before diving into the heart of the matter, I really wanted to thank all the incredible mentors I've had the chance to work with for the past month. So thank you, Ocean, of course, Clara, Helen, also Harrison, and Mathilde, and Maria, of course. So all really great mentors, and everything that was achieved was a very close collaboration throughout the month with the mentors. So without further ado, let's dive into the matter. So as Oshin just said, the goal of the project was to improve the accessibility of charts in the domain of Earth science, especially for weather forecasts. So on the right, you have this kind of weather chart features that here for a visually impaired person, they would not be able to distinguish anything. The problem is that a lot of information is explained with these kind of charts in the research fields. That's a big problem because this domain is very multi-dimensional. It's very hard to interpret things just from text or just from the data. So we go through these charts, and we don't take a lot of time to explain them completely, fully, and making them basically accessible. So this challenge was targeting that to create a very detailed and very thoughtful description that would kind of replace the visual. More concretely, we wanted to create an extension of the EarthKit library ecosystem. So EarthKit, and here EarthKit plots, is the main item tool to plot and interpret the meteorological data. So scientists would use this library to plot the data that they have acquired, and we discussed the systems to acquire data a bit earlier. And of course, these weather charts will touch thousands of different users, and it's critical to make the alt text generation capability very easy to access. So the target was to extend EarthKit plots for that reason. Today, it doesn't exist, and there are no other tools that I've seen that do that automatically. So we have created our custom solution based on large language models. So here is what we're going to see. In a moment, we'll see the concrete achievements. We'll see how we ran a user study to evaluate the performance of the system with the expert validation. In the third time, we'll see the system architecture, how we did it. And finally, we will see what could be the future development of this project. First, the achievements. So here is what the integration looks like today. So for those familiar with the EarthKit, you recognize EKD and EKP or EarthKit data and EarthKit log. These are two libraries from the ecosystem. So you would get the data, you would plot the figure, and you would create our agent, which is our system of two LLMs plus things that will generate the description. So you see quite a concise API. What I can say here is that you see we have a LLM provider, which is Gemini, so the Google's models, and we also input the model name. You can choose among many of the main providers. You can even have your own custom LLM and use the solution all the same because we have created a client and instructions to build a server. But here it just sends the HTTP calls, so you can use whatever LLM suits your need, and the rest will not change and will work the same. So here would be what the model does. So the system does this. When you call the generate out description function, you would input these kind of visuals that we saw before, but it's unblurred, plus the actual data, and it would generate this description on the right. So at this point, I could show you the whole descriptions, but I would need 3 screens, I think, because it's very detailed. There are a lot of steps because we made that for Earth scientists, so it's as detailed as we could make them. And we tried to target these characteristics to structure the descriptions. We tried to have them follow a certain structure. With the overview, you see some context for the dates, the longitudes, latitudes, the ranges, some visual aspect of things. Having a smooth flow of information and good language, and of course, being scientifically accurate and relevant. More on that later. At this point, I could show you the whole description, many descriptions on many charts, but you would probably not be able to interpret them because I was not, and I'm not sure I would be, because I'm not an expert. So we asked experts to validate the work and also, of course, to drive the wood. And that's what I will be focusing on today to show you what they thought of the system. So we ran a user study, as I was saying, and the user study consisted of 8 experienced Earth scientists with a median year of experience of 12 years. So very advanced Earth scientists. I think the most experienced was 40 years of experience, and the least was 5 years of experience. So just 8 scientists, but very experienced in the domain of interpreting weather chart descriptions. So during this study, what we asked of them was for 10 chart description pairs to answer 2 types of questions. The first type was binary acceptance. Would you accept to share this description with a visually impaired scientist? That was our human threshold to say, okay, can we put it in the real world, essentially. The second type of evaluation that we asked them to do was to rate on the 5 of 1 to 5, 1 being bad, 5 being excellent, the quality of the descriptions along 4 dimensions that each evaluate different aspects of the descriptions. These quality criteria are coherence, fluency, consistency, and relevance, and more on that later. They also could leave qualitative feedback for each chart description pairs optionally, and they did, and it was very interesting. And they could also leave at the end of the study to maybe for general feedback or to improve the way we run the study or whatever. And in total, we had 8 individual evaluations. You see the calculus. So here for the first type of results, you see on the, let me try that. Yeah. So on the y-axis, you see the acceptance rate. So they accept to send that to end users, to blind or visually impaired users. And on the x-axis, we just have the different charts. So you see that the average rate was 65% of acceptance. So quite good among, well, I would say to what I was expecting because it was very experimental. And we'll see more details just after. But there is discrepancy. Definitely 1 and 8 were very, very good descriptions, and 9 was absolutely bad. So we may wonder what drove the quality so high for certain charts and what was driving it so bad for other charts. A second point that is interesting is that the experts didn't agree on all the charts in the same way. We had two groups of evaluators. So here, what changed with the previous chart is that the x-axis is for the experts. So you see we have two groups. There is the first group of evaluators that was super happy with all the descriptions, and the others. The two others did not like at all any of the descriptions, essentially. Whoops. Yeah, did not like the descriptions. So this is again a question that we want to answer. Why is that? Small comments when we remove what appears here to be outliers, but maybe they're not. We had a small pool of evaluators after all. It raises the average acceptance rates to 81.7%. So what we learned here was that globally, people liked our system, and by that I mean experts. But there was a wide discrepancy. Some charts were good, some charts were, one chart was very bad, description was very bad, and overall it revolves around 65% of acceptance rate. Now, let's dive into the quality criteria evaluation that answers some of these questions. So here you have a small explanation of the different criteria. Coherence and fluency are for language-oriented quality evaluation, whereas relevance and consistency are for data-oriented evaluation of the quality. So coherent structure, fluency, language correctness, relevance, importance of the data that was extracted. So this is dependent on the situation, on the context. And consistency is just accuracy, how truthful was the data extracted and present in the descriptions. So here you see the results for that. So for each criteria, you see the scale of 1 to 5, 5 being better than 1. You see that the linguistic criteria, which were coherence and fluency, are scored much higher than the other ones, but still they are all above, I would say, the baseline of 3. So of course, what we used in the backend are large language models. So we all know that they're good at language. So here it really shows. And what was hard was extracting the data, making it relevant, making the relevant interpretations. And we put a lot of work there, but still there are margins of improvement. So bear with me with this chart. I know it's a bit hard to read. I will explain it. But basically, on the y-axis, you see the chart IDs. And on the x-axis, you see the different quality criteria. And here, the numbers and the colors, green being the best and red the worst, are the average scores for each chart, for each criteria, average over all the evaluators. So, oops. So the 1867 charts, the descriptions, were the one that had the highest acceptance rate. So when we isolate them, what do we see? They basically have good scores across all the criteria, but they have one score usually that is above all the others. So all scores above 4 and one or more scores above 4.5. So this is interesting to know what made them good. It's basically they're good at everything. But what is maybe more interesting is what made the chart description 9 so bad. And here we see we have the reason. It's because the consistency and the relevance were very low, meaning that the data that was extracted and interpreted was wrong, essentially. So everyone was did agree with that. So we have a clear signal. Now we try to predict the acceptance of a description with machine learning based on the scores of the evaluators. Why for? To know the importance of each criteria in driving the acceptance of an evaluator. So here is what we see. First, on the bottom right there, you see the F1 score for the two models that we've used, logistic regression and like GBF. And you see that they are quite high. The score goes from 0 for worst to 1 for best. So here we are at 0.9-ish. So the models very accurately predict the acceptance of a description. So we have good predictors. So second thing is the different scores don't have the same importance at all. We see that the relevance and consistency are the criteria that most predict the acceptance. Simply said, the evaluators put way more value on how factual and relevant the data in the description is compared to the structure or quality of the language. So to sum up what I just said, we had very strong linguistic qualities in our descriptions. We faced some data challenges. Even though the score were quite good and the acceptance rate was quite good, we clearly see where we can improve the system. It's the data extraction and interpretation of things. And we also have some idea if we wanted, for instance, to filter the descriptions for end users, not to just throw in the wide every description. We could use a machine learning model that would evaluate from the criteria evaluations, filter the models. And essentially what we will need is a good evaluator to score the descriptions. And we'll see more on that just after. So now you may wonder, that's good, but how did you do that? We had three main components in the system. There were the data extractors, the generator, which is a large language model, and the evaluator, which is also a large language model. First, the data extractors, they parse the data, which were input in the system with the grep files, or because we use the EarthKit data library, there are some level of abstraction, so you are quite flexible with that. But we just use the grep data in our case. It extracts the info from the data itself. So for instance, we worked a lot with temperature and pressure. So for pressure, you might, with some deterministic heuristics, define where are the pressure centers, what are the intensity of the pressure events, and for temperature, maybe some kind of detection of the heat wave flows or something along those lines. And it's also in charge of structuring these extracted data and making it available for the LLMs, basically in a string, formatting in a string. The generator is the large language model that is in charge of analyzing the data and the chart image. So it's multimodal. You have the data that is in the prompt that we extracted before and the image. And it will create from that the natural language descriptions. When it has evaluator feedback, it will also iterate on its previous description to generate an improved description. And the evaluator is the one that scores the quality of the descriptions generated from the generator along the 4 dimensions that we discussed before, which were relevance, coherence, and the 2 other. It will verify it's above or below some thresholds of quality that we predetermined. On the R scale, it was 4 for all criteria. And it will provide its scoring rationales and some feedback improvements fed back to the generator so that the generator can improve. And we would do that over a couple of iterations. So these are the components. If we take a look at the flow of information, this is what it looks like. We input the data from the RIP file. The extractors will digest this data and transform it into something more actionable. It will enrich the 2 LLM prompts, both the generator and evaluator, and then it will go into the generation and evaluation loop to reinforce the descriptions. We have 2 cases afterwards. Maybe we met the quality thresholds that we have predetermined. Then all good, we send that to the user. Or we had not enriched the max iterations. So we add warnings in our description at the beginning, like, okay, this was auto-generated. Well, this is always inside, but this is bad along this dimension. You may be more careful even than the usual, and do that with while being careful. Of course, we could simply also decide not to send it to the user or whatever. So this is what the flow looks like right now. So now, what about the future developments? You may have guessed a lot of them already, but basically, we haven't had time to analyze all the qualitative feedback that was provided by the experts. So there is a lot of information and a lot of insights for improvements that can be found there. So we will need to analyze the qualitative feedback as well. We saw that the data-oriented quality metrics were the lowest and was what was driving the bad results sometimes. So we would need to work on the data extraction to make it more powerful, more accurate, and more tangible from experts' advice. And finally, because we have just run a user study based on like the scientifical part of the descriptions, are they scientifically sound and good? We would need to evaluate the accessibility of the descriptions, meaning running a user study with actual users, blind or low vision users. Thank you.
Thanks a lot, Romain. Very interesting insight into about how this works. Any question? Johannes.
Maybe I missed a lot, didn't get it, but how does this work with the quality test? How does it have its own quality?
So there is a large language model that has the same instructions as the expert evaluators that we have run the study with. And it will say, okay, from the instructions I have, this is the score I give to the description.
And it works well?
It works like the most difficult part. So the thing is, the experts themselves disagreed a lot between them. So of course, it's just one way of evaluating the system. It does identify critical errors and fix that way, but we don't have the clear signal and clear instructions to say this is the perfect description. So in that sense, we cannot say this is the perfect evaluation or whatever. We would need way more feedback from experts, and we would also need them to agree between them to have like one very accuracy quality. But it does some rounds of improvements, yes.
Not yet. Is okay. Step out.
So I have a question regarding the number of iteration with the IP of the response. So for example, if you iterate highly on a topic, but we can export to new iterations. increase?
There is a diminishing returns on the loops. So actually, the first one is valuable. The second one is usually way less, and sometimes you don't have any. So it really depends on the chart, the difficulty. Also, sometimes when we extract the data with the data extractors, there is a lot of incoherence in what we extracted because we're just using heuristics. So if the data is contradicting itself between the different extractors, the description will be bad. And then we have we go over 3 rounds of improvements, and then if we have not seen anything, then we just stop. So you can put as many iterations as you want. Personally, I see no improvements after the second round of improvement.
Yeah.
Okay, thanks for the interesting project. I'm wondering what maybe I missed that part. The analyzer, does it just get the picture, or does it also get context that the picture may sit it? So it's there is already a description, or does it go and look at the web for similar pictures and look at the descriptions of those, or does it really just look at the visual at the imagine stuff?
Not just the visual, but not the web. It has access to the information extracted from the data itself. So the data was used to generate the plots, and both the plots and the data are fed to the system. But it doesn't go over the web. And also, it's not dynamic in the sense that if the first information that was extracted was not enough, we don't do another round of extraction. It's not dynamic in that sense.
I was curious about another truthful example for the server text filter. Sometimes the user might just want like a visual description, not any meteorological interpretation, and sometimes they want everything. Is that a option if you choose, or is it always like set in stone and safe?
It's definitely set in stone because our users were Earth scientists, and from the feedback we gather from experts, this is the direction they wanted us to take, essentially. So you could definitely change that very easily with changing the prompt and just saying, I want a quick overview, or I just want to know this thing. But here it's really a system made for Earth scientists and making it as detailed and as accurate as possible because we thought it was the hard case. If you can make that, you can make it less complex, essentially.
There's like to gather more like expert opinions in the future.
Yes. We have still a lot to interpret from the qualitative feedback. And we saw that there were 2 groups of evaluators, and we definitely need to know why the second group didn't like most of the descriptions. So there is a lot of work that is possible, yes.
I think you could try like a blindness study with like some control feedback.
Yeah, so
That they don't like the other ones.
yeah, so that's a very good point. So it raises two things. So first, the accessibility study that I was speaking about was to target the real end users, which are unsighted people. And because I've done a bit of my studies on that, I know that blind folding people doesn't really represent the actual blind people. They have completely different systems of interpretation. So we would need to run it with actual blind people and not try to blindfold.
Oh, I do mean like literally mindful people. I'm like blinded in that the experts couldn't know whether it's AI generated or human.
Yeah, true. Yeah, so there's that too. Comparing, well, maybe we could extend that and run a study with a gold standard that would be human generated description and compare it to actual other descriptions. So that's a very valid point. And we didn't do that because we had very few descriptions to work from. But yeah, if we had more data, we would run that type of comparison. Yeah.
Good. Any other questions? Good. Then thanks. What